Okay, so we have been looking at the resolution refutation method, and we have found a method that is sound and complete and semi decidable. That is the best you can do with first order logic. But let us look at the complexity side of it essentially as to how long does it take to find a proof essentially, or sometimes what is even the length of the proof. Now, it turns out that in 1985 one guy called Haken he showed that he showed for propositional logic okay. The one thing about propositional logic is that it is decidable as opposed to first order logic, which is as we have seen semi decidable. All the methods that we have seen, forward chaining, backward chaining or resolution method, can run into infinite loops. But in propositional logic, because you are always working with a finite set of formulas or finite set of clauses, eventually you will exhaust all possibilities and you will say that okay, I am not able to prove it essentially. In first order logic, we cannot say that we are not able to prove it. For example, we try to show that is 0 less than 0, and we were not able to show it given the knowledge base that we had, and it kept asking a question whether 1 is less than 0, whether 2 is less than 0, whether 3 is less than 0, and it could obviously go on infinitely along that sequence. In propositional logic, one can terminate and say yes, no other possibilities exist. So, we can this thing, but what Haken showed was that given a set of clauses that he could produce a set of n clauses, the shortest proof is exponential in length. Which means the number of derivation steps that you do is exponential in n essentially. Okay. So, I should really say in n. So, if the proof itself is exponentially long, then the proof finding process, because remember that we are doing some kind of search, we may do some useless inferences, we may do some useless applications of the resolution rule and so on, before we come up with the final proof. If the proof itself is exponentially long, then the proof finding process will be even more difficult essentially. So, the first thing we understand is that it is not the task of finding a proof is not going to be easy in first order logic, because even in propositional case there are formulas for which the proof is exponentially long. And sometime I had mentioned earlier that if you take a formula in general first order logic and you convert it into clause form, the length of the formula itself will increase essentially. So, the number of clauses can go up essentially. You must also keep in mind the very well known result by Stephen Cook, who actually earlier had shown, and he defined the notion of NP completeness, and in fact, NP completeness, the whole concept is centered around the SAT problem, and he showed that the SAT problem is NP complete. Now, remember that the SAT problem is essentially a propositional logic problem, where you are given a set of formula in clause form or in some form actually. But generally when we talk about SAT, we talk about 2 SAT and 3 SAT and so on, and so anything which is more complex than 3 SAT is in the NP complete set essentially, which means that it is a hard problem essentially. So, in practice, if you are talking about trying to show that something is satisfiable, or if you are trying to show that something is unsatisfiable, which is a kind of the other side of the phase, you can run into exponential times essentially, which is why very often we use randomized methods. So, this is just to highlight the fact that it can be hard trying to find a proof in first order logic essentially. Now, there was one approach which is due to mathematician called Herbrand, and this is called Herbrand's theorem. So, before I state the theorem, let me first give a couple of definitions. We have something called the Herbrand universe. So, you are given a set of sentences, those sentences will refer to certain objects. So, some constants in the domain essentially. So, let us say the constants in the domain are A and B, just for illustration purpose. The Herbrand universe is the names of objects that you can construct using the constants that are available in the given set of sentences and the function symbols that are available to you. So, if the constants given to you are A and B, then the Herbrand universe is A and B. Then let us say if f is a function given to you, f of A and f of A and so on essentially, maybe g of A, if g is another function given to you, g of f of A, all kinds of things, whatever is possible you construct essentially. Then the Herbrand base is instances with elements of the Herbrand universe substituted for variables. So, the Herbrand base is a set of sentences that you arrive at by substituting for variables all the constants that you can invent. Okay, what are the constants that you can invent? Those are the ones that are given to you to start with, for example, A and B, and by applying function symbols like f of A and f of g of A and so on and so forth essentially. So, if you substitute those elements of Herbrand universe into the formulas, then you essentially come up with a set of sentences which are without variables, in other words which are propositional in nature essentially. So, of course, the first hope was that can we now treat this as a propositional logic problem, but obviously there are no free lunches in computing anywhere available. You can see that the moment you have a function symbol, and if the language is unrestricted, in the sense that a function symbol can apply to any term, then you will have an infinite number of terms. So, you started off initially with let us say we are talking about a set of students and there are let us say 15 students. So, we started off with 15 constants and then some function definition like let us say father of or whatever function you can think of, or best friend of, if that is a function. Then you could define more terms. The whole idea of first order logic was to not go around making infinite statements and so on. But unfortunately, if you have function symbols and you keep applying them in an unrestricted fashion to even a small set of constants, you will end up generating an infinite Herbrand universe, in which case the propositional version of the language, which is the Herbrand base, will also be infinite essentially. So, we will not get the benefit of working with a finite propositional set of sentences for which there is termination essentially. But what Herbrand's theorem says is that if H is the Herbrand base of a language or a set of sentences S, then if H is unsatisfiable, then so is S. Or in other words, it suffices to show that if you can, working with the Herbrand base, if you can show that the set of sentences is unsatisfiable, then you have shown that the original set is also unsatisfiable. Now, obviously, people have thought of various ways, we will not get into those here. Is that, for example, you could work with a typed kind of a language in which you cannot apply functions indiscriminately. For example, the function successor of, you could apply only to numbers essentially. The function, let us say, father of, you could apply only to humans, and so on and so forth, and then you could try to restrict the set of Herbrand universe. Or if you are happy or lucky enough to work with a set of sentences in which there are no function symbols, then obviously you can convert everything into propositional case and try to solve it essentially. So, that is an approach for those of you who have studied planning, has been taken in by the planning community, where they say that instead of having all operators which have variables, we can convert them into what they call as ground operators. So, you come up with a propositional case and then try to solve it essentially. But that does not work essentially. So, we also look at search heuristics. I will just mention a couple of them here, and then we will move on to looking at a subset of FOL, which is more tractable essentially. Remember that our resolution method says that they choose a set of clauses or choose two clauses resolve them, add resolvent to the set, and you keep doing this essentially, right. Just take two clauses, resolve them, add the resolvent to the set, then pick two clauses and so on essentially. The question is which clauses, because everything really depends upon that. And if you happen to choose the right clauses, then you will come up with a derivation quickly and so on and so forth essentially. So, there are a couple of strategies that people have talked about. So, one thing you should observe is that if I take two clauses, let us say C1 length is equal to 3, then and if let us say length C2 is equal to 4, then the resolvent could be as much as so you will remove one disjunct from C1 and one from C2, because they will cancel. So, the remaining you will have to keep. So, 2 plus 3, which is could be 5. And what do we want? We want the null clause is equal to 0 essentially. There are 0 elements in the null clause essentially. We want to work towards the null clause. So, it would not seem like a good idea to work with two clauses which are long and produce a resolvent which is even longer essentially. It may not really help essentially. So, one strategy is called unit preference. That as long as possible, choose one of the clauses should be of length 1. because then you can see that if you choose one clause of length n and the other clause of length 1, then the resolvent will be of length n minus 1 essentially, because one of them will get cancelled essentially. So, then you will end up with smaller and smaller clauses. So, that is a unit preference strategy, that as long as possible choose one of the clauses to be a unit clause. If you happen to choose both as unit clauses, it means that you have come to an end of the procedure, right. Another strategy is called set of support. This says that one of the clauses must be a descendant of the goal. Remember that the goal is negated. What is the intuition behind this? The intuition behind this is that the reason why our set of formulas is unsatisfiable is because we negated the goal and added to the set, and then it became unsatisfiable essentially. So, whatever contradiction that we want to derive must come from the negated goal essentially. So, set of support strategy says that one of the clauses must be a descendant of the goal clause essentially, or the goal clause must be one of the ancestors of the thing. In fact, we will see an example, an instance of this strategy in a short while essentially. Another approach is to work with a subset of the language, and this subset is called Horn clause subset. That you do not work with a full language, but you do not allow certain things to be said essentially. And as we will see, what you do not allow to be said is the disjunction. You can't make statements which kind of have uncertainty about that. You cannot say that color A is green or color B is green essentially, because then it is going to lead to complexity. What are Horn clauses? Horn clauses have at most one positive literal. Which means a Horn clause has the structure of not P, this could be in first order case, but I am just writing some symbols here, or not Q or R, or you could have something like R as well. You are allowed to have this thing. Or you could also have something like not S or not T. Now, these two clauses are called positive, or also called definite. And such a clause is called a negative clause. So, in the Horn clause subset of the language, you are only allowed in every clause, remember it is in clause form, which is CNF form, every clause can have at most one positive literal. So, it can have 0, but it cannot have more than 1 essentially. So, things like green A or green B are not allowed, because this has got two positive literals essentially. And you can also get a feel that these are the kind of statements which led to incompleteness of forward chaining and backward chaining essentially. If you start talking about the disjunction, then that is a problem that can happen. Now, let us revisit the resolution rule. With Horn clauses. So, let us construct a small table where the input clause can be positive or negative. So, there are two clauses we are selecting. So, let us take two positive clauses and we are talking about Horn clauses, right. What will be the result of resolving two positive clauses? So, let me just take an example. So, P or not R and R or not P. Well, let me use something else, not Q. Now, these are two positive clauses, right. This is positive and this is positive. You can see that one of the there are only two positive literals in these two clauses, both are positive. So, one must have one positive literal and the other must have the other positive literal. One of them will get cancelled because that is what the resolution method says. So, in our example this will get cancelled with this and what we will get is P or not Q and the result is positive. So, when we resolve a positive clause with a positive clause, we will get as a result a positive clause. If we resolve a positive clause with a negative clause, for example, if we take a positive clause, let us take the same one P or not R and let us take a negative clause. Let us say it must contain not P because we want to be able to resolve something and it has something else not Q or not S or something like that. So, we will end up removing that single positive literal which is there and we will end up with a formula which is not R or not Q or not S. So, if we resolve a positive clause with a negative clause, then we will get a negative clause as output and by symmetry the same if we resolve a negative clause with a positive clause. And we are talking about Horn clauses. See, non-Horn clauses may have more than one positive clause essentially, which means that the positive clause, if it had two positive literals and you resolve it with a negative clause, you would still be left with one essentially. So, you could end up with positive literals, but if you are working with Horn clauses, then this is a table that we are constructing, that if you resolve two positive clauses, you will get a positive clause. If you resolve a positive clause and a negative clause, you will get a negative clause. What about the case of resolving a negative clause with a negative clause? It is not possible because you need a positive literal to be able to this thing. So, this case does not exist at all essentially. Okay. Now, the next thing we want to show is that for Horn clauses, and if goal is negative, then there always exists a derivation in which every resolvent is negative. Okay, this is something which somebody has proved, but we will not try to prove it. Instead, we will just try to look at an example and sort of justify this statement essentially. So, let me just work with an example. Let us say we have three negative clauses. sorry 3 Horn clauses. And let us say I have a derivation in which I resolve this with this. So, C will go cancel with not C. So, I will be left with not E or not F or D, and then if I resolve this with this, I get not E or not F or not E. So, I have a negative goal, but in my derivation I have a positive clause essentially. And what one can kind of demonstrate is that we can transform every such derivation into one which does not have a negative, which does not have a positive resolvent essentially. So, the basic idea is this, that look for in some sense the lowest positive resolvent, lowest meaning which occurs latest in the derivation, and remove that essentially. So, how can we remove this particular positive resolvent? We can remove it by doing the following derivation instead, that instead of resolving that with this, we will resolve this with this. So, here D will cancel with not D. So, we will get not F or not C or not E, which is a negative clause, and then we will resolve this with this. So, not C will cancel with C. So, we will be left with the same clause there. Now, you can see that for this clause with this is the goal clause that we are talking about, goal is negative. We have two possible derivations, in one which has a positive resolvent along the way, and one which does not have one along the way essentially. So, you should just take it for granted that or you can try to work out an algorithm which will do this. Pick the lowest meaning the latest positive resolvent, and by doing something like this, because there will be 3 parents involved, that is why I have just drawn that subset here. If you just redo the derivations amongst those 3 parents, instead of deriving this positive clause on the left, you can derive the negative clause which is shown on the right, and you will end up with the same negative goal that you have to derive. So, you can always have a system derivation in which there are only negative clauses essentially. Now, we look at, again we are focusing on Horn clauses, and we want to look at something called an SLD derivation. So, just for the sake of this stands for selected literals, this stands for linear pattern, and this D stands for definite clauses. So, remember definite is just another term for positive clauses. Now, to jump ahead a little bit, when we talk about positive clauses, if you think about this a little bit with Horn clauses, you are essentially talking about a Prolog program. Because what is a positive clause? If you look at a positive clause like not P or not Q or not R or S, This is just another way of writing P and Q and R implies S, which is in Prolog you would have written like S if P Q R. So, a Prolog program is essentially a set of definitive definite clauses essentially, or positive clauses essentially. And this SLD resolution is a special derivation which says that which has the following structure. So, let me first draw the structure and then I will talk about it. So, let us say we have a set of clauses D 1, D 2, D 3, D n minus 1, D n and good loss. So, let us say that all these are positive. So, you can think of it as a Prolog program and this is a negative clause, which you can think of as negated goal. So, remember that in the resolution refutation method you take the goal, negate it and add it to the set of clauses and then you do the resolution. Now, an SLD derivation is a derivation which has a structure that every resolvent is a negative clause, as we have shown that that will be the case. We have not shown, we have sort of illustrated that can be the case. And the parents of every resolvent is the last clause that was derived, the last resolvent and one of the definite clauses. So, which if we draw a diagram would look like this. So, I will take the negated goal and resolve it with one of the clauses, and remember that a positive and negative will give us a negative clause. But now, in SLD derivation I must use this as one of the input clauses. So, one of my two clauses will always be the last clause that I have generated, the last resolvent that I have generated. So, I can only take a child of this. So, I can take for example, something from here and observe that I have to take something from the set of definite clauses, because I need a positive and a negative clause to be able to resolve essentially things. I cannot anyway go back to one of the negative parents. So, this will be another negative clause. Then I have to use this and maybe this one I will get another negative clause and so on. So, I will ask you to look at this, one of the programs that we have written for plus or something like that, and observe that this whole process is essentially backward chaining. Because we start with the goal, then this becomes a sub goal. So, if you identify negative clauses with goals, then essentially you start with a negative goal, then you come with the sub goal, then with the next sub goal and then the next sub goal and so on till the process terminates essentially. So, you can actually think of this as a Prolog program with backward chaining essentially. What is a interesting thing that we know, which makes this interesting, is that this property holds that, and remember we are talking about Horn clauses, that if we can derive a null clause from a set of clauses, and remember that we are interested in the resolution method because we have shown that it is complete for deriving the null clause, then So, this is for Horn clauses. And if this SLD derivation we denote it by this SLD derivation, this statement is what is interesting. It says that, and we have sort of tried to hint towards this by showing that we can always transform a derivation in which there are positive resolvents into one which has only negative resolvents, and then we are making this claim that if we have this kind of only positive definite clauses which is like a Prolog program and one negative clause which comes from the goal, then the process is like backward chaining. So, we studied Prolog as backward chaining, but now you should be able to identify backward chaining with SLD derivation with Horn clauses essentially. And what Kowalski and other people showed was that this thing holds, that if you can derive the null clause using any kind of derivation in Horn clauses, then you can derive the null clause using SLD derivation which is Horn clauses. The nice thing about SLD derivation is that this is a linear process. You do not have too many choices essentially. Computational complexity comes out of choices, which clauses to pick essentially. In SLD derivation, this has been frozen for you. You can only pick the last resolvent as one of the parents to resolve, and the other parent will automatically, well, you may have choice as to which of those definite clauses to pick, but you can only pick that which resolves with one of the negative literals in the parent essentially. So, if my parent looks like if my parent is, let us say, not R or not S, some negative clause, remember that we are always generating negative clauses, then I can only put that positive clause which either contains R or another positive clause which contains S essentially. I cannot randomly pick other kind of clauses. So, first of all, I am forced to go through a linear process, that I must pick as one parent the last resolvent that was generated. The other parent, which is choice, is almost automatic. It is almost automatic in the sense that, for example, with this parent not R or not S, maybe there are two separate clauses which you can pick, but the choice is limited to removing some of those negative clauses essentially. The price that we have to pay for this ease in complexity is that the onus is now, as we have seen when we were looking at backward chaining, is on the user to write the rules in a particular fashion essentially. We have said that Prolog will always choose the first one that matches in the order in which you write them essentially. So, I will leave you with this, and I will ask you to do a little bit of reading about this. With this class today, we have finished the first 7 chapters of Brackman and Levesque, and though not necessarily in the order in which they are given in that book. And we have also finished chapters, more or less we have finished chapters 12 and 13 of my book, which are the 2 references that we are using essentially. So, we have kind of dealt with general theorem proving in some sense, and we are done with that. In the next class, we will look at ways of, we will come back to the representation issues, and we will try to see that instead of trying to search for clauses to make inferences with and so on, why not put together relevant pieces of information together in one place in some sense, and we will look at this notion of frames which was introduced by Minsky, which was in turn the basis for what we now call as object oriented programming essentially. So, we will have a change of flavor in the next class onwards essentially.